He was named as the SDSC interim director in June 2009 and appointed to the director position in September 2010. He has been there serving SDSC for almost now 11 years. He's a distinguished professor of physics at UC San Diego and a globally recognized astrophysicist. He's a pioneer in using advanced computational methods to explore the universe and its beginning. In this capacity, he has directed the Laboratory for Computational Astrophysics, a collaborative effort between UC San Diego and SDSC, resulting in the NGO community code for astrophysics and cosmology used worldwide. Many of you might be also using the NGO code at your supercomputing centers. He's the author of over 300 research articles in diverse areas of astrophysics, including star and galaxy formation, the evolution of intergalactic medium, as well as numerical methods. And Professor Norman's work has earned him numerous honors, including Germany's prestigious Alexander von Humboldt Research Prize, IEEE Sydney Furback Award, and several SPCC Challenge Awards. He's a fellow of the American Academy of Arts and Sciences and the American Physics Society. He holds an MS and PhD in Engineering and Applied Sciences from UC Davis. And in 1984, he completed his postdoctoral work at the Max Planck Institute of Astrophysics in Germany. From 1986 to 2000, he held numerous positions at the University of Illinois in Urbana as an NCSA Associate Director and Senior Research Scientist under Larry Smarr, and as a Professor of Astronomy. From 1984 to 1986, also he served as staff member at the Los Alamos National Lab. Dr. Norman is the PI of the two SDSC's leading HPC systems, Comet, and the very recently, which has been awarded, which is the Expanse. And today, that's what will be the focus of this talk, and he will be talking Computing Without Boundaries on Expanse. So let's give a hearty welcome to Professor Norman to this virtual event. And Professor Norman, please share your slides and get started. The floor is yours.
Thank you, DK, for that wonderful introduction. Let me go full screen. Okay. Everyone seeing my slides?
It is, yeah, it has come out, yes.
Okay, excellent. Thank you. Well, it is really a pleasure to be here with you today and talk about our latest system at SDSC called Expanse. And I promise you I will explain what I mean by computing without boundaries in a few slides. Now, if we were all together in a room and if I were presenting from my laptop, I would show you this amusing time-lapse video of the assembly of Expanse. The hardware showed up a little over a month ago in these trucks, and it was subsequently assembled, and with everyone wearing masks. And so this is the first deployment we've done in the midst of a pandemic. And of course, our university, like every other university, has put some very stringent social distancing rules in place. And so it was quite a challenge to get this system put together with social distancing and masks and cleaning. But we got it done. And I'm not showing this video because I tried it out yesterday and it just looks terrible over Zoom. It just doesn't work. So we'll be posting this before too long and you'll be able to see it for yourself. Okay, but the Expanse is there. Dell handed the hardware off to us last week, and my team is now installing software on the system, including, of course, MVAPITch. Here's some shots of the system. Let me just give you the basic facts about the project before I get into the architecture and the target audience. The full title of the proposal is Computing Without Boundaries, Cyber Infrastructure for the Long Tail of Science. This is the result of an NSF solicitation for advanced computing systems and services, adapting to the rapid evolution of science and engineering. It was a Category 1 award, a capacity system, and our program officer is Bob Chaddock. I'm the PI of the project, and my co-PIs are listed here: Ilkay Altintas, Amit Majumdar, Mahidar Tatneni, who will be speaking later today, and Sean Strandy, who is also the project manager. It's a $10 million system, and we will be operating it with a budget of about $2.5 million a year. It's a Dell cluster attached to Eon storage, and the technology inside is coming from AMD, Intel, NVIDIA, and Mellanox. And this is our first water-cooled system, at least since the craze of the late 90s or late 80s. So this is a liquid-cooled system, which of course also complicated the installation somewhat, because now you have to plumb the cluster, not just power and cool the cluster. So this is the project on one slide, and I'm going to come back to this slide in a few minutes. I just want to explain to you what we mean by computing without boundaries on this slide. So it's a very nice HPC cluster, and I'll get to the details of that. But what we mean by computing without boundaries is there's a variety of remote cyber infrastructure integration as a part of the project. We will enable cloud bursting as a routine part of the workload through the Slum scheduler. We will integrate with remote heterogeneous resources to do edge computing and projects that require distributed workflows. And as we have for over a decade, we will integrate with the Open Science Grid. The thing that is rather unique about this project is we continue to push the boundaries of how we operate the system. So this will involve composable systems for the first time through OSG, high throughput computing. As always, science gateways will be supported. We will have regular support for interactive computing, for notebooks and so forth, full support for containerized computing, and as I said, cloud bursting. So we think of Expanse as a nexus in a distributed, integrated cyber infrastructure, and it can reach out to a variety of resources. But before I dive into the details of Expanse, I just want to look back a little bit over my 11 years as director of the center and PI of 3 projects. Expanse is really the latest incarnation of SDSC's evolving HPC strategy, and I want to look at how we got here. It is, in some sense, a culmination of a decade of lessons learned. But, you know, in brief, what we've done is to adapt to user needs. We've innovated on the hardware, the software, and the operations of the system, and we've taken some risks. And we have tried to skate to where the puck is going to be, to quote Wayne Gretzky. This is one of my favorite concepts. And I think we've been pretty successful in that. So in the next few slides, I want to take a brief review of the systems that have come before Expanse and talk about what we tried to do differently and what were the lessons learned. And this is essentially my contribution as SDSC director over the last decade. So let's start with Flash Gordon. We call it Gordon, but the proposal actually was entitled Flash Gordon. We didn't want to get sued by the you know, the media company. So we just shortened the name to Gordon. It was a data-intensive HPC system. Down here in the lower left, you can see the years of NSF production. But the specific innovations that I would like to highlight are listed here. First, it was the first system to have a large amount of flash SSD built into the memory hierarchy. So we had IB connected flash 300 terabytes, which at the time was a lot. We also had node local flash. So we had flash in two places. We also deployed ScaleMP's software called VSMP, which aggregated servers into what we called super nodes. So you as a user could have a 256 core shared memory system image at your disposal, which we thought would be very handy for data analysis. It featured a dual rail 3D torus, and we actually routed the MPI traffic over one of the rails and the Lustre IO over the other rail, such that they would not interfere with one another. The file system at the time had an amazing 100 gigabyte per second bandwidth, and all of this together is what we envisioned a data-intensive HPC system to look like. Gordon was also the system where we did our first experiment with the Open Science Grid, and where we actually got it integrated in time to support a large data analysis campaign from the Large Hadron Collider. And as you'll see, we maintained that OSG connection ever since. So what were the lessons learned? First of all, the computational chemists love flash SSD on node for their Scratch IO. This was not foreseen. This was a result. And consequently, most of the computational chemists in the TerraGrid program flocked to SDSC. We were the first in TerraGrid Exceed to do storage allocations, that is to say, non-purged project storage. However, we had surprisingly low demand for the VSMP supernodes. So let me say a little more about what that is. What it is a virtual shared memory across physical nodes. And our standard setup was a 16-way supernode, meaning 16 physical nodes were aggregated into a 256 core virtual SMP. And that had 2 terabytes of RAM and 8 terabytes of flash. And we thought that this would be a great platform for porting and running threaded big data analytics software. We thought at the time that there was not a lot of data analysis software that had been implemented with MPI. And so let's just present a large shared memory environment for that. The surprisingly low demand was the result of the fact that most NSF researchers did not have big data. And this was a real surprise for us because this system was deployed in the era where big data was the buzzword of the day. You all remember that. You know, every 2 years we get a new buzzword. Right now it's AI and machine learning. But 10 years ago, it was big data. And so that was an interesting lesson learned. And consequently, in our subsequent system, we did not deploy VSMP software. So the next system I'd like to talk about is Trestles. This was our first experiment serving the long tail of science. So this was a long tail capacity system pilot. It only operated as an NSF resource for 2 years. And then we gave the cluster to the University of Arkansas, where it's still running, I'm told. But the innovations were really in how we operated the system, not how we architected it. Well, it was architected to support capacity jobs. We kind of shortchanged the fabric because we knew that we were going to be serving primarily small to medium jobs. So we didn't need full bisection bandwidth across the cluster. It was also architected to support gateway access. So Ethernet to every node and so forth. It also included node local SSD like Gordon. So here you see the first example of carrying a successful lesson forward into the next architecture. But operationally, we underallocated the system to ensure good turnaround. And we limited the maximum job size in terms of the core count. And we implemented scheduling policies that favored long tail jobs. In the old days, when HPC meant computing across the entire machine, scheduling policies often favored the largest jobs. Well, we turned that on its head, and we favored single core and single node jobs so that they would get through quickly. So what were the lessons learned with Trestles? Well, first, long tail users are really out there. There was huge demand for capacity systems. And here on the right, I'm showing a figure that was part of the Trestles proposal, where we analyzed a year's worth of TeraGrid workload, 2011, and we got this chart. And what this shows is let's just look at this curve here with the dots. This is the amount of SUs charged as a function of the job size in cores. And you go up to 50%, a fully 50% of all jobs charged were 1,000 cores or less. This curve here is just the cumulative. And you see that 99% of all SUs charged were done at 2,000 cores or less. And so, as we'll see in the next slide, this really informed our design for the Comet system, which is basically Trestles scaled up. Because we underallocated the system, our expansion factors were excellent. Users loved the high throughput. This was at a time when gateway access was becoming more and more important as an access mechanism. It would attract non-traditional HPC users. And we noticed that there was an enormous potential to support many more users and many more jobs. Which brings us to Comet, which is our current workhorse at SDSC. Comet is basically taking concepts from Gordon and Trestles and scaling it up. But then we added a couple of other innovations. So I describe it as a virtualized hybrid long tail capacity system. It went into production in 2015, and you got to realize that the proposal for Comet was written in 2013. So if you think back to the world in 2013, and you think about virtualized computing, virtualized HPC, nobody was doing it, really. And so this was quite innovative. We also woke up to the fact that more and more people are using GPUs. So this was our first system with GPUs. We added additional hardware so that we could host dozens of gateways. So we envisioned this system as basically a server for gateways. The virtual cluster capability exploited Mellanox's SRIOV, and we were able to achieve native IB speeds over a virtual private network. What this virtual cluster capability allowed us to do is to carve out a piece of the physical cluster and hand it over to a team such that it looked like bare metal, but they were actually sitting on top of a virtualized environment. And the Open Science Grid took advantage of that and created a full-up OSG cluster inside of Comet. And like all virtual machines, it can be spun up and spun down. It can be made to be whatever size the load demands, and so forth. So you're not carving up the machine statically, you're able to do it dynamically based on demand. We adopted all of Trestles' operating policies. We implemented shared node scheduling so that, for example, the nodes on Comet have 24 cores. We could be running 24 single core jobs through our scheduler. And the GPUs also can be used in, the GPU nodes have 4 GPUs each, that they could be used either in shared mode or dedicated mode. We pioneered the 24-hour trial account, and we did the first Exceed deployment of Singularity. I mean, a funny thing happened on the way to putting Comet into production. We designed it with this virtual cluster capability, which was implemented using KVM. But by the time by 2016, Docker containers and Singularity were emerging as a new way to do computing. And so we were the first to deploy Singularity. So what were the lessons learned with Comet? Well, we're still learning those lessons. It's still in production. The first is there was an unforeseen higher demand for GPUs. Again, remember we wrote the proposal in 2013. And at the time, we had a huge debate about whether we should put GPUs or Xeon Phis on the system. And we decided for GPUs because there was, software out there that was using GPUs. But of course, this whole, machine learning, deep learning revolution subsequently took off. And so what we did is we doubled the number of GPUs on Comet through a supplementary request to the NSF. We find that users love Comet, especially chemists, material scientists, and biologists. Comet has node local SSDs. I mean, we don't deploy a system anymore without node local SSD. It's just the thing to do because these applications generate lots of small files. Gateways are the dominant usage mode. Our goal for the 5-year project was to serve 10,000 unique users. You might say, well, that's not a big number, but at the time, if you looked at a typical Exceed system, it would serve about 1,000 users. So we wanted to do 10x that through gateways, and we achieved this number in the first year. So we revised our long tail goal, 50,000 users by the end of the project, and we are currently at over 80,000 unique users. So here you see a bunch of the team with Tom Tabor from HPC Wire. We got a couple of awards, one in biology, one in for gravitational wave science. There's Frank Werthwein, the executive director of the Open Science Grid, who was instrumental in bringing in LIGO as a project. There's Mahidar Tatneni, who will be speaking to you later. There's Amit Majumdar, and there's Sean Strandy, the project manager. Okay, well, let me just say a word about MVAPITCH at SDSC. First of all, Amit Majumdar and Mahidar Tatneni have been collaborating with DK and his team for a long time on NSF-funded projects, and all of our systems to date have deployed in MVAPITCH2, and Expanse will deploy MVAPITCH2 as well as MVAPITCH2X in GDR for reasons that will become apparent. So let me come back to Expanse and talk about it in a little more detail. I'm going to skip over the cluster and the storage for the moment and just come back to this point, the computing without boundaries, which is achieved and supported through this list of innovative operations, which I've already mentioned. So let me put more meat on the bones here. And first, just give an overview of the cluster and the operations. So what is Expanse? It is a 728 node, 2-socket AMD compute system. We're among the first Exceed sites to deploy the new AMD EPYC Rome processors, 64 cores per socket. So one node will have 128 cores, which is pretty astounding. Altogether, it has 93,000 CPU cores, which is about twice the core count of Comet in half the space. Of course, these racks are getting denser, more energy hungry, which is why we need the liquid cooling. The cluster will also have 52 4-way GPU nodes based on the V100 with NVLink connectivity inside the node. Based on the benchmarks we've run, and Mahidar Tatneni will be talking about this in more detail, we expect more than 2x throughput over Comet and a 1.8 per core improvement over Comet's Haswell processors. We have had relatively little difficulty getting our acceptance applications up and running on the Expanse test nodes. So we expect a smooth transition from Intel to AMD. The system is being listed as an available resource for the upcoming Exceed Allocations Review Committee, and that would be for a January 1st start date. We hope to go into production October 1st, and we'll have operations for 5 years with a 5-year follow-on system anticipated. Okay, so you can think of Expanse as Comet on steroids, but adding a couple of new usage modalities to the mix. So Comet itself will conclude NSF operations at the end of March 2021. Expanse will advance science and engineering discovery. Here's a few statistics about Comet. This slide is already out of date. Way more than 40,000 unique users, over 1,200 publications, 2,000 institutions supported. 2,000 research, education, and startup allocations, 400 institutions, lots of scientific discoveries, including being part of the first detection of gravitational waves by LIGO, as well as the first detection of merging neutron stars, which resulted in opening the era of multi-messenger astronomy. IceCube is also computing on Comet and comes to us via the Open Science Grid. In fact, the Open Science Grid is the way that large instruments get their computing done on Exceed. And because so many of those simulations are single core or single node, they are part of the long tail workload. So Comet's historical usage is a pretty good indicator of the science we expect to support on Expanse. Here you see that more than half the pie is molecular bioscience, materials research, and chemistry. Physics, basically engineering and astronomy are the next wedge, and then a variety of other disciplines as well. Okay, so now we get into some dense slides, and I'll try to brief these at a high level. So here you see the basic numbers. You get some other numbers. There's 256 gigabytes of RAM on a node, and there's a terabyte of NVMe on each node. So if you think about, if you go all the way back to Gordon, the node local flash was, as I recall, 80 gigabytes, mostly for system software. Now we've got a terabyte, mostly for applications on each node. The V100 GPU nodes, they have 1.6 terabytes of NVMe on each node, which is great for staging data sets for deep learning and whatnot. We always deploy large memory nodes, 4 of them, 2 terabytes of RAM per node. And these will also be the Rome AMD processors. So the way we've designed the cluster is a little interesting and new for us. We call it an SDSC scalable compute unit. Every rack is identical, and there's 13 racks. So each rack contains both the CPU nodes, 56 of them, as well as the GPU nodes. So each rack is a hybrid system. There's one HDR switch at the top of the rack. And we are using HDR 100 gigabit per second non-blocking fabric. And as I mentioned, direct liquid cooling. So there's a few more details on the GPU and CPU nodes. Of course, the NVIDIA V100s have all these tensor cores available for deep learning workloads. There's a little bit on the network. Now, what I didn't say about Comet, which is also true for Expanse, is because it is designed to be a long tail system, we limit the maximum job size to 1 rack. 1 rack's worth of cores. And on Comet, that was a little more than 1,700 cores. And if you remember that TerraGrid workload analysis I showed you, 98% of all jobs were 2,000 cores or less. And so we designed Comet such that one rack could run 98% of the jobs, at least in 2011 jobs. Now, one rack of Expanse has over 7,000 cores. And our maximum job size will be 7,000 cores. Well, it's actually 56 times 128. It's a little more than 7,000. And so one rack of Expanse is a pretty darn powerful supercomputer. And we have 13 identical racks. The fabric, the inside a rack is a fat tree full bisection bandwidth, HDR InfiniBand. We have some oversubscription between racks because we do not envision and we do not support jobs that run across the whole system. Okay, so then where does Expanse live in the grand scheme of things? It's connected to a Lustre file system, a 12 petabyte system, IB connected, and then it's also connected to a Ceph object store. The object store is new in terms of a system deployed at SDSC. We think of it as a short-term archive or where computational campaigns will keep their data, over multiple years. It's also useful for the composable systems and for staging data to the public cloud. So if you recall that we will support cloud bursting from Expanse, this object store will be a good place to transit data to the public cloud. UCSD has a campus DMZ, the Prism network, where actually the Open Science Grid comes in via that network, comes into SDSC. And there's a variety of external networks that we appear with, including the Pacific Research Platform, ESNet, Internet2, Scenic, Exceed, and we have an Amazon Direct Connect at a gigabit per second. So as Mahidar will talk about a little later today, we've done a lot of initial benchmarking of our acceptance applications on the AMD hardware, and everything looks great. So now let me talk about some of these new capabilities, these new modalities. First is integration with the public cloud. So this is something that we have prototyped on Comet. And so we are simply going into production with this on Expanse. So first of all, why would you want to integrate with the public cloud? Well, one way that we think about it is if there's a new instance type in the cloud that we don't have on-prem, we could make it look to the user as if we have that on-prem and it's integrated into Expanse through our scheduler. So let's imagine, I don't know, a crazy suggestion. What if Amazon deploys NVIDIA A100s in the next 6 months? Well, we can make it look like Expanse has A100s by just providing a new queue in Slum. Now, the researcher will have to bring their own money to purchase those cloud resources. That is not part of our budget. But in terms of integration, we will do that such that the cloud is seamlessly supported. In other words, I call this hide the cloud. Make it look like it's just part of Expanse. You just put you set a flag inside your Slurm script, and you say, yes, I want these jobs to run on the cloud. I want this instance type. And the rest is done for you, including the data transfers to and fro. So this capability was prototyped on Comet with some NSF support. We did some in-house development to Slurm, and we're leveraging a multi-cloud scripting software called Terraform from Hashicorp. And I'm sure some of you are familiar with this. This capability will be demand-driven in the sense that we're going to see who shows up with what applications that want to burst to the cloud. And so we're not going to, on day one, support all clouds and all resource types in the cloud. But we're going to see what it is people want to do. There's a variety of options for moving data back and forth, including remote mounting of file systems, using caches, and moving data with the job itself. Okay, so that's cloud bursting. The second new modality, and this is really in the spirit of what we've done before, is composable systems. So what is a composable system? It is a distributed software workflow that involves containerized applications that are scheduled and mapped to resources using Kubernetes. And so the way that we're going to manage Expanse is using the Bright Cluster Manager, which has a software product called CM Scale, which can talk to both Slurm and Kubernetes. And this allows the cluster manager to create a Slurm partition and a Kubernetes partition. And this can be dynamically adjusted based on demand, on workload. So we imagine that you will have regular jobs running through Slurm on this part of the cluster, and if we happen to have a composable system application running, that part would be running on another part of the system, talking to edge computing devices and or the cloud as need be. Good. So a few operational words here. So first of all, this capability was developed under other NSF awards to UCSD, not SDSC per se, but one of them is the Pacific Research Platform, and the other is Chase CI. And our co-PI, Ilkay Altintas, is a co-PI on those awards. And so Ilkay will be leading the composable systems effort. The way it'll work is a researcher will request a composable system application as a part of an XRAC request, and then the advanced user support will be provided to that project if it's allocated. And this advanced user support is part of our operations funding. So for those of you who are familiar with the ECSS part of Exceed, think of this as a mini ECSS funded out of the Expanse project to support composable systems. Now, you might be saying, okay, I hear what you're saying, but I still don't know what a composable system is. Can you give me an example? Well, here's an example. This is operational now. This is the Wi-Fi fire weather monitoring and prediction system developed by Ilkay Altinch's group. And what this does, it's a system that takes a variety of data inputs, in this case, sensors on towers in Southern California, weather forecast, model data, data from aircraft that are measuring fire perimeters, satellite data on terrain and vegetation, and feeds it all into a distributed workflow that is able, in the end, to predict the spread of the fire, given fuel, topography, and wind conditions. Now, you might say, well, where does this need a supercomputer? Mostly it doesn't need a supercomputer, but when you're actually doing the fire modeling, and you want to do that more or less in real time so that the firefighters can do scenarios, that's where you need an HPC system to support, some of that stuff. So this distributed system would, be mapped to a variety of resources. And if it needed HPC, part of it would be running on Expanse. Okay, so I'm actually looking at the clock, and I've just been blabbing on here like there's no tomorrow. Yes, Expanse will be integrated with the Open Science Grid, and this is a diagram that is far too complicated to go into. Just say that in the case of the Open Science Grid, the user is called a virtual organization, and a virtual organization has multiple users inside of it with multiple jobs. And there's a lot of plumbing that needs to be done in order to take advantage of our shared scheduler capabilities, as well as accounting. You have to account for the jobs that are running on the system. So in terms of user support, it will be just like normal. We are an Exceed Level 1 resource. We have a 6-month overlap between Comet and Expanse operations, which should provide plenty of time for Comet users to migrate to Expanse. We are standing up a new program called HPC at MSI, which is targeting minority-serving institutions, and researchers at such institutions will be able to make directors' discretionary requests on allocations, and those will be processed rapidly, and our support staff will help those researchers. So finally, if I want to use Expanse, what do I do? If you are familiar with Exceed, then you know what to do. You go to the Exceed website, you submit an allocation request. Remember that you will be able to choose from a trial request, which will be processed in 24 hours, a startup allocation, an education allocation, or a research allocation. Those all have different, levels of proposal effort. And in general, we would recommend starting with a small allocation and working your way up. If you happen to have a campus champion on your campus, you can also work with them to learn about how to do all of this. You go to the Exceed user portal to request an allocation, and it's a very, very nice system. As I said, the upcoming XRAC will consider requests for Expanse, and startup and trial allocations will be available at production launch. So There are 3 resource types associated with Expanse that you can request. There is the Expanse cluster, which is the CPU part of it. There's the GPU resource, and then project storage. And by early next year, we will take Comet's file system and convert it to a Ceph object store for those applications. So here's just a few dates. Hardware has been delivered. The hardware installation is complete. The SDSC team is installing software now. We hope to have an early access period in September. Those of you who are interested in early access, please email me or mahidar.neni. We'll be doing a variety of training events in the coming months so that you can learn more about it. So thank you very much for your attention. We look forward to seeing you on Expanse. We do have an Expanse website at SDSC, which you see listed here. And the last slide is just the cast of characters and our vendor partners in this project. And thank you very much. I actually didn't leave that much time for questions, but I guess we have 4 minutes.
So Mike, thanks a lot again. There are a few questions in the QA box. I also allowed Mahidar to be a panelist also. Either of one of you can open up that Q&A box and you can answer. Otherwise, I can read the questions.
Okay, let me do that.
Hi, DK. This is Mahidar. I don't see.
Open up the Q&A box.
I can read them out.
Okay. Yeah.
So the first question is in Gordon, flash SSD at 2 levels. One is local SSD. What is the other?
Oh yeah. So Gordon,
Mahi, can you speak up a little? Your voice is a little low.
Oh, hold on a sec. Let me just bump my mic up. Is that better?
Yeah, perfect. Thank you.
Okay, great. So yeah, Gordon had 2 levels of flash. Basically, the bulk of the flash was in IO nodes. We had 16 300 gig drives in each IO node, and we had 64 of these IO nodes. I think that's, I think that's the right number. And basically, we had ICER mounted devices on each node. So basically, each of those drives would be mounted on a single compute node via ICER. So that was the primary way people got access to Scratch local SSD. It was local as far as the user was concerned, but the device was actually remote. That was one, and then the node local SSD was primarily for like OS and temp space and things like that. So we had that also based on SSD.
Thanks, Mahi.
2 additional questions. Hari, you can read those. Yeah.
Sure. So the next question is, what was the type or brand of Lustre storage system that you guys used?
So all our Lustre storage, I think going back to Gordon and Trestles, was basically the storage is from Aeon Computing. It's a local vendor here in San Diego, and they've deployed some really big systems across the country. So we get the storage from them, and we build our own Lustre file system. So the open source Lustre.
Sure. One more question. What is the Ceph storage system used for?
So the idea for Ceph is going to be new in Expanse, and one of the things we noticed with a lot of people trying to do like compute spread out across various sites is kind of object store kind of capability requirements. Some people have looked for that, especially in the data space. That one use is going to be basically like a staging ground for moving data to the cloud or moving it to some other place. Or also, like in the composable systems case, it might be the place where you pull the data out from when you're computing. So you could be doing an S3 call, for example, to pull the data into your composed system, because we won't have a file system that's mounted across all of the components of the composed system, because some of it we don't control, right?
So thanks again, Mahidhar and Mike. If there are any other follow-up questions, audience, please feel free to post them on the Slack, and Mahidhar and Mike and others will be able to follow up. Okay. So thanks a lot again.
All right.
For the
Well,
wonderful talk.
thank you. Thank you. It's my pleasure.
So we'll then move to the next talk. Let me introduce the speaker.